Hello everyone, welcome to online machine learning session. In today's session, we will have a detailed look on the Bayesian classification. So we will start by having the basic definition of Bayesian classifiers, and then we will see that how it is built on top of Bayesian theorem, and then we will also study an example through which we will try to understand that how Bayesian classifier is built on Bayesian theorem and how it is used in order to solve classification problems. So the Bayesian classifiers are statistical classifiers. They can calculate the probability that a given sample belongs to a particular class. So on the basis of probabilities, it first calculates probabilities, and on the basis of those probabilities, it tries to see that in which category or in which class a particular sample belongs to. So a Bayesian classification is based on Bayes' theorem, which is a classical theorem in statistics and probability. The Bayesian classifiers have exhibited high accuracy and speed when applied to large databases. So it is a very good plus point due to which many people have used Bayesian classifiers, because as compared to other classifiers, Bayesian classifiers can give you very good accuracy rate as well as in very less with very less computation time, because in most of the cases when we apply other machine learning classifiers on large databases, then they take a lot of time, and sometimes it becomes impossible to bear that computation cost. But the good thing of Bayesian classifiers is that they not only provide us good accuracy rates, but also they can be applied to a large number of databases. So that's why the use of Bayesian classifier is still very prominent, and even on large databases, people are applying Bayesian classifiers with good accuracy. So now let's see initially that what is Bayes' theorem. So as we know that if we have a sample of data which is represented by x, so let's suppose that our data samples consist of a number of fruits, and those fruits are red in color, and the shape of those fruits are round, and this data sample is basically represented with the variable x. Now we can draw our hypothesis, which is represented by HA here, and we can say that according to some hypothesis, the hypothesis states that the x belongs to a specified class C. So C represents here to some kind of a particular class through which this sample x belongs to. And here, for example, we can say that this C class is an apple, and our sample x is an apple. For classification problems, the target is, or the goal is, to determine the probability of h given x, where h is our hypothesis and x is a sample point. So we want to determine the probability, that how much is the probability that some hypothesis h is what is the probability of an hypothesis h when we have a given data sample. The probability that the hypothesis h holds given that the observed data sample x. So we are trying to determine this in our classification problems. So now we need to understand two terms related to probability. One is the prior probability and the other is the posterior probability, and these two terms are very necessary to understand if you want to understand the Bayesian theorem. So the prior probability, the probability P of h, and remember that h is a hypothesis here, so the probability of hypothesis is called the prior probability of h, right? So this is the prior probability of our hypothesis, and it states that the probability that any given data sample is an apple regardless of how the data sample looks like. So in our prior probability, we are assuming that any given data sample will be an apple. So the probability is that the given sample will be an apple, and regardless of the fact that how does it looks like. The probability of pH given x, which is the hypothesis with the given sample x, is called the posterior probability, right? So p of h is the prior probability, p of h given x is the posterior probability, and it is based on more information. So in this case we have much more information as compared to prior probability, right? Because we have now the information of the given sample, so it is based on more information than the prior probability, and because prior probability was independent of x, because this is not depending upon the sample x, but the posterior probability is depending upon the sample x. So we can say that the posterior probability, if we consider that the data samples be fruits and those fruits are described by their colors and shape, then we can say that x is a data sample that is red and round. So this is our example which we are considering here, and we are supposing that x is equals to red and round, and our hypothesis h is that this x, which is red in color and round in shape, is an apple. Then we can say that the probability of h given x is the probability that x is an apple given that x is red and round. So because this is representing by this equation, here we are saying that the probability that x, which is a data sample here, will belongs to an apple category given that the x is red and round. So the Bayes theorem is basically built on these prior and posterior probabilities. And the Bayes theorem provides a way of calculating the posterior probability. So it can be given by this expression. We can say that the probability of h given x, which is our posterior probability, it can be calculated by probability of x given h into probability of h divided by probability of x, right? So if we use this expression, we can calculate the posterior probabilities. The probability of x given h is the posterior probability of x given h. So it is the probability that x is red and round given that x is an apple, right? So we have defined it here that with the given hypothesis, the data sample x is the posterior probability of x, right? And again we know that p of x here is the prior probability of x, which we have defined in previous slide, and it is the probability that the data sample is red and round. So this is basically the Bayes theorem. Now let's have a quick look on the proof of Bayes theorem, which I hope that many of you have already known. So let's have a quick look on its theorem. So the posterior probability of the fruit being an apple, given that its shape is round and its color is red, it can be represented by probability of h given x. So it is h and x slash x, right? So that is, what does it means? It means that the number of apples which are red and round, right? So those are divided by the total number of red and round fruits. Because x is representing red and round fruits, so we are basically dividing this with the total number of red and round fruits for our specific example. So since p of h given x is equals to h and x slash total fruits which are red and round, then we can say that probability of x is basically x slash total fruits of all the shapes and sizes, and hence we can say that probability of h given x is equals to probability of h and x slash probability of x. Similarly, we can say that conversely p of x given h is equals to probability of h and x slash p of h, and if in this way, if we use these equations which we have calculated, we can have this proof here, right? So this is basically a brief description and overview of Bayesian theorem. If you are not familiar with it, then please have a look on the basic statistical theory of Bayesian theorem. So now let's coming back to our example or our classification domain which we are trying to solve with Bayesian theorem. So Bayesian theorem is the basis of our Bayesian classification, and the studies comparing classification algorithms have found that the simple Bayesian classifier is comparable in performance with decision tree and neural network classifiers. So it is a very important point here that the two very commonly used classifiers, which are decision trees and neural networks, which we will see in our upcoming lectures, that people are giving preference to naive Bayes over these two classification algorithms because they are comparable in performance, and on the other hand they are giving very good results with less computation cost.